Let's look once more in detail at the scientific method. Here we see a schema, the classic scientific method, as from a textbook. But I think we already know enough to see that the scientific method in this stereotype form is not fully accurate as to how science works. According to this archetypal version, scientists make observations, they pose questions about their observations, look for patterns in the data, and then suggest a hypothesis. They use the hypothesis to make a prediction, and then they perform a test or another experiment or more observations to test their prediction. And the outcome is either that the test does not support the hypothesis, in which case they revise it or perhaps reject it completely, or it does support the hypothesis, in which case they continue through the loop to make additional observations and continue to test them. And after sufficient testing and affirmation of the hypothesis, perhaps it elevates to a law of nature. Well, that's the theory of the scientific method. We know that in practice it's not quite that simple. And we've seen earlier about some of the qualities of science that make what science is versus what science is not. Generally, good science seeks robust explanations for observed phenomena that rely solely on natural causes. No mystical, supernatural, or unnatural motivations or mechanisms. Science progresses by creating and testing models that explain observations as simply and efficiently as possible. That's another premise of the scientific method called Occam's razor, after a philosopher from the 14th century. The idea here is that there may be more than one explanation for any set of data, and if you're faced with a choice, you choose the simplest explanation. Why? That's an actual interesting question. Why should nature be simple? A scientific model must make testable predictions that force us to revise or abandon the model. But there are secret sauce in science, extra ingredients that we can't accommodate with a simple flowchart. There's the role of luck and persistence. Science is a human activity, and humans are flawed, so science is sometimes flawed. But at the end result of all this endeavor, we do end up with some theories, some laws of nature. That is a model that has survived repeated testing and is considered to be robust enough that it's unlikely to be in error. But it's always worth questioning our assumptions, and the assumption of Occam's razor that the simplest theory is correct is one that it's really worth looking hard at. In this cartoon, we see that many theories are simple but wrong, and perhaps the world is more complex than we think or have any right to expect, and so the best theory might be a very complex theory. Hallmarks of science: seeks explanations for observed phenomena relying on natural causes, progresses through the creation and testing of models that explain the observations as simply as possible, and makes testable predictions about natural phenomena. If the predictions are not borne out, the model must be revised or abandoned. These are indeed the hallmarks of science that any field of science will agree upon, but how they're executed in practice is, of course, quite an interesting question. Because science, as I've said, is a human pursuit, and scientists are flawed, and scientists have prejudices, and scientists have emotions, and sometimes these feed into the work of science. Maybe they shouldn't, but they do. There's also another thing which is an amusement to some scientists, and this is a joke, this cartoon, but scientists don't operate in a vacuum. They exist in the culture of science and the culture of academia, typically, working in universities or research institutes. We've already seen in the early history of science with the ancient Greeks there was a tension between two fundamental ways of knowing the universe. The empirical way of learning, by experiment, epitomized by Aristotle, and the purely theoretical way of learning about nature, by thinking about it, by theories and hypotheses, and this is the idea of Plato. Now, in this caricatured view, mathematics is more pure and more fundamental than physics, and philosophy, of course, is the most pure field at all, because it's not bound by data or observation or the messiness of the real world. So as we talk in this course about the philosophy and history of science, we recognize that philosophy is a foundation stone for science, but it's also working independently of science. It is not bound by data. At some level, it's operating at pure concept level, and so it may not be right. We also have science that deviates from proper principles, and we need to be able to recognize that.
Sorry. Sorry, nobody down here but the FBI's most unwanted.
Agent Mulder, I'm Dana Scully. I've been assigned to work with you.
Oh, isn't it nice to be suddenly so highly regarded? So who did you take off to get stuck with this detail, Scully?
Actually, I'm looking forward to working with you. I've heard a lot about you.
Oh, really? I was under the impression that you were sent to spy on me.
If you have any doubt about my qualifications or credentials...
You're a medical doctor. You teach at the academy. You did your undergraduate degree in physics. Einstein's twin paradox, a new interpretation. Dana Scully's senior thesis. Now that's a credential, rewriting Einstein.
Did you bother to read it?
I did. I liked it. It's just that in most of my work, the laws of physics rarely seem to apply. Maybe I can get your medical opinion on this, though. Oregon female, age 21, no explainable cause of death. Autopsy shows nothing. Zip. There are, however, these two distinct marks on her lower back. Dr. Scully, can you ID these marks?
Needle punctures, maybe. An animal bite. Electrocution of some kind.
How's your chemistry? This is the substance found in the surrounding tissue.
It's organic.
I don't know. Is it some kind of synthetic protein?
Beats me. I've never seen it before either. But here it is again in Sturgis, South Dakota. And again in Shamrock, Texas.
Do you have a theory?
I have plenty of theories. Maybe what you can explain to me is why it's bureau policy to label these cases as unexplained phenomena and ignore them. Do you believe in the existence of extraterrestrials?
Logically, I would have to say no. Given the distances needed to travel from the far reaches of space, the energy requirements would exceed a spacecraft's capabilities.
Conventional wisdom. You know this Oregon female? She's the fourth person in her graduating class to die under mysterious circumstances. Now, when convention and science offer us no answers, might we not finally turn to the fantastic as a plausibility?
The girl obviously died of something. If it was natural causes, it's plausible that there was something missed in the post-mortem. If she was murdered, it's plausible there was a sloppy investigation. What I find fantastic is any notion that there are answers beyond the realm of science. The answers are there. You just have to know where to look.
That scene, a classic in TV history, is from the pilot of The X-Files. Now in the series, Mulder, called Spooky Mulder by his colleagues, is right. There are aliens out there. They have been abducting people. They have been visited on the Earth. They have been stored at government facilities, and it's been kept secret from people. But in the real world, Mulder isn't right. In the real world, Scully is right, and she's the skeptic. So skepticism is at the heart of science, as we've seen. Now, this leads to a societal issue. Science literacy is actually low, measured formally at around 10%, and as it's easy to see by picking up any paper or watching TV or videos or YouTube, the pop culture is awash in all kinds of pseudoscience, magical thinking, superstition, and supernatural or irrational belief systems. And let's not forget the lure of an irresistible conspiracy theory. We look here at crop circles. Now, I was growing up in England when the first crop circles appeared, and the people who actually did it, two workmen on a farm who just pressed down wheat in geometric patterns and then laughed about it in a pub afterwards, they were outed within weeks. But that didn't stop the thing from taking off, from crop circles propagating around the world and being seen in the western plains of the US and Australia and Canada, more and more complicated, feeding into conspiracy theories of how aliens had shown geometric proofs of math theorems we hadn't even developed, and it just took a life of its own. People forgetting the antecedents that it was just a simple hoax. So, this is the issue of science, that we do have science, but we also have fake science, pseudoscience, superstition, conspiracy theories, and other things that essentially combat or beat against science. Unfortunately, it's the job of scientists to take this seriously and do their best to counter the tide. But science as an act does have real problems, and we go back to the philosophy of science to realize that there are issues behind science that have to be dealt with. We start with the problem of observation. It's the fact that there's no such thing as pure data. So a core component of what we would call a common sense view of science is that it's impartial, unbiased, free of theory, and observation plays the pivotal role, the Aristotelian view. That scientists don't approach their subject with any preconceptions. They just make observations about what happens in the world and build the observations into a backdrop of theories that describe the world. The observations are the data that the scientific theory appears to explain. But in many different examples, visual observations are not just like camera photos on a retina. Depending on how you look at it, in the picture on the right, below, Westerners will see two different staircases. But in the culture of some African tribes that don't have the tradition of representing three-dimensional objects two-dimensionally, they report just seeing a bunch of lines. Whose observation is right if observation has a cultural dimension? What's the data here? Now, this is a very simple example using visual observation, but we can extend this to more complex observations, and the same issue is there. Observation is also theory dependent. Another important point is there's no such thing as theory-independent observation, just as there's no such thing as pure data. Because observations, even simple ones, presuppose a theory of the world and the object under consideration. And what you choose to observe depends on your theory, because that's how you test it. So with incomplete or imperfect data, which is always the case in science, how do you decide if it's the data that are in error or the theory? Think of the failure to observe stellar parallax and how that didn't bring down the Copernican model. It just led to the hypothesis of the stars being unobservably far away. That's a rather strange process in science if you think about it. So, the Copernican model predicted the size of Venus should change appreciably in a year, but observers on the Earth didn't see the changes. However, to say Venus does not change size during the year implies a theory, which says that the size of small light sources can be measured with the naked eye, and that's not true. Modern theory now explains why observations with a telescope are needed, and they do show that Venus changes size significantly. But we can see this issue of observation when we're always working at the frontier of our data and our capabilities, and the data is not pure or perfect. There's also a problem called the problem of the ideal world, idealization. The idea that science studies the real world is a core part of the common sense view of science, but there are qualifications to this. Scientists engage in idealization. That is, you need to get away from the real world to simplify it enough to understand how it works. This is well understood in natural science. For example, a chemistry experiment does not consist of digging up rocks from your back garden and mixing them with water in the tap and seeing what happens. It consists of mixing pure material, say sodium, with pure water, even if total purity is impossible. But if science is about studying the world, it seems this shouldn't be legitimate. How can you claim to be studying the world when you have experiments that are made up, or unreal material that you've manufactured in a lab that doesn't match what's in the real world? Now, when it comes to the example we're using, chemistry or physics, this is not a problem, because we understand the real world is complicated and full of complicating factors. If you engaged in the world with all its complexity, you'd never get anywhere. What you need is to make the problem simpler. You can try to factor out interfering factors, such as to get to the basic truth of the world. Water out of a tap contains not just H2O, but chlorine and many other trace chemicals. And if you put sodium into that water and it starts sparking, is that due to the water or the chlorine or any of the other unknown trace elements in the rock or the water? You have no way of knowing. So there's an important sense in which science isn't about observing the world. It's about trying to understand the world by dealing with idealized versions of it, versions which incorporate assumptions you know are not true. And the best example of this, which we've already seen in this course, are thought experiments. The extreme form of idealization, which is heavily used in physics and astronomy, is a thought experiment where you don't actually do an experiment at all. For example, the experiment below, seen on the lower right, negates Aristotle's physics. It's related to the idea of how fast different objects drop. Galileo imagined dropping a cannonball, and then he imagined the cannonball broken in two with a thin spindle of metal holding the two halves together. Since it's still one object, obviously the two pieces are connected and the thing falls the same way the whole cannonball would. But you can make that spindle so small that it disappears, and then you have two objects. And logically, and by extension in this thought experiment, those two halves should fall the same way as the whole cannonball did, which is a negation of Aristotelian physics that says that large objects fall faster than small objects. So is this valid, this thought experiment? It's actually correct. But do we know it's correct when we never actually do the experiment? Another problem is the problem of induction. We've seen that one of the key things that science does is generalize by saying all copper conducts electricity. But that's of course based on observation. And it's based on the fact that we have a bar of copper that conducted electricity one time in the lab, and then another bar of copper that also conducted electricity at a different time, and so on. And when you've done this enough times with enough different types of copper, enough different experiments, you can make the general statement that all copper conducts electricity. But David Hume, the Scottish philosopher we've already encountered, also an economist and historian, he was called, for example, by the Stanford Encyclopedia of Philosophy, the most important philosopher ever to write in English. He pointed out the problem of induction. Inductive reasoning, inference, is sort of more of the same reasoning, concluding that a general statement must be true on the basis of a large number of individual statements. So given a large number of observations of how copper conducts electricity, scientists can correctly conclude that all copper conducts electricity. But Hume says the required justification simply doesn't exist. We're not even entitled to conclude that the next piece of copper will conduct electricity, much less that all pieces will do so. Now, logically, it's correct. We sense a resistance in common sense to this, but it's the problem at the heart of inductive reasoning. It depends on the assumption that the future will be like the past, and that's not always the case. And the best example of this, a humorous example, is called Bertrand Russell's turkey. Bertrand Russell told the story of a turkey that was fed every day at 9 a.m., and so eventually, over a period of time, inductively concluded that they would always be fed at 9 a.m. every morning, until one day the sun rose, it was Thanksgiving, and the turkey was killed for the dinner table. Well, that's the danger of inductive reasoning. So you have to assume your conclusion that you're trying to prove. It's circular reasoning. It's begging the question. And although in the practice of science we use induction, we have to recognize a logical problem at the heart of this method. The paradox of induction is worth looking at in a little more detail. For instance, every raven you see is black. You're entitled to form a hypothesis that all ravens are black, and test it by seeing if every raven you encounter in the future is black, affirming your hypothesis. The problem is that in logic, the complement of the statement if A then B, which is if not B then not A, must also be true and must support the hypothesis. Therefore, observing any non-black thing that's not a raven is support for the original hypothesis. And so we can go around observing all manner of non-black things that happen to be non-ravens, and logically, and in philosophy and induction, this is supporting our original hypothesis that all ravens are black. But that just seems silly. How can observing any non-white, non-raven thing tell us about ravens? Or, to use a different example, take the hypothesis that all swans are white. We inductively conclude that after observing a lot of swans. Even if they're rare, does the discovery of a single black swan, and they do exist, invalidate the whole hypothesis? And if it doesn't, how do we modify the hypothesis? Obviously, induction is not quite as simple as we thought at first glance. We consider the role of theory. In a very general form, there are things that are in the universe and things that aren't. We imagine our theory explains some fraction of the things that are. We're not so full of hubris that we imagine we can explain everything that is in the universe. Our goal in theory, in science overall, is to explain everything, to have a theory of everything that is. But how do we distinguish a theory of everything from a theory of too much? A theory that explains all the things that are, which of course we haven't yet encountered, but also happens to explain some things that don't happen, that don't actually exist. That's a humorous example, but it gives an example of how the reach of science runs into the practicality of doing science. Looked at in a different way, here are all the things that are and all the things that aren't. There are also things that are possible that don't actually happen. There are things that we can imagine, and our brains are wonderful tools for being human. Our brains can imagine in this Venn diagram most of the things that are, but maybe there are things that actually happen that we can't imagine. We can also imagine many things that are possible that don't actually happen, and we can imagine things that don't happen. That's what creativity is all about: fiction, poetry, art. And so the question is, how do we distinguish these realms? Because imagination and creativity are part of scientists as well as doing science. And that's the end of this module.